Yeah. R equals rho L over A. Where's my paint program? Come on. Open. You can do it. My web browser must be eating up all my memory. There we go. Now, if you want, you can try and remember the formula and spit the definition from the formula. So you have R equals rho L over A. So what are you looking for? It's the rho, resistivity, and that's equal to RA over L.
Okay.
So you could say that the resistivity is the resistance offered by a conductor per Now what I'll do is, to make the English a little bit better, I'll divide the top and bottom by A. So I have R over L over A. So I can have resistivity as the resistance offered by a conductor per unit length per unit cross-sectional area. KJ, what does he go for? I'll read it all out, Fahad. Resistivity is the resistance offered by a conductor per unit length per unit cross-sectional area. And I should perhaps say electrical resistance, but you get the idea. What does he say?
Resistivity is numerically equal to the resistance of the sample of unit length and unit resistance area at a certain temperature.
I probably should say at a constant temperature, yeah.
Why did you divide by A?
I didn't need to. Ignore it.
Because you just want to get that number.
I just wanted to have, it's just nice having the per twice. Because if I had the A up the top, then I would have to say ohm meters, and it doesn't read it well. Okay, the B part now. Right, can I go down to the B part?
Yes, please.
Yeah, so what you have here, in this experiment, you're changing, can you see in the experiment? You're changing the length of the, what material is this? Unknown material, is it? What the heck is that word? I've never seen that in my life. Constantan wire? No, but that word, a length L of constantan wire.
Constantine.
Is it really, KJ?
No, constant.
Can you Google that word to see if it's a real word? Are you Googling? Did he just accidentally put AM at the end? I don't know.
Constant wire.
It is it a material?
Also known as Iruka, advanced and very use of copper nickel wire usually consisting of 55% of copper and 45%.
It's 55% copper and
45% nickel.
so it's actually a material then. It just looks so weird spelled out. Tan is at the end. Constantan. Right, anyway, enough about that nonsense. So, in the table, what have you got? You have Look, guys, what have you got on the table? You have the length, the current, and what do we want? Resistance. So let's write down our formulas. We know that OR equals rho L over A. We also know we have our VI-OR triangle. So, what else? Oh, do we have enough information?
Yeah, we know the V constant.
Oh, and the V we know is constant, yeah. Wait, so if we know the V and we know the I, then the OR is just V divided by I.
Yeah, we don't need to know the rho.
So we don't need to, we don't care about the length.
Yeah, we don't even have the rho.
Huh?
The rho constant.
No, we don't, but we might need that later. Anyways, okay, so can you just read out, this is length in meters, and this is current in amps, and this is resistance in ohms. What are my currents? Currents.
2.08, 1.58, 1.40, 1.40, 1.12, 0.99.
Okay, and my lengths, we might as well put them in. Oh, they go in 0.25s, do they?
Yeah.
Right, so what's the formula for resistance? Well, I just wrote it there in the triangle, it's V over I. And what's the V?
1.2
divided by I. So you don't have to write all the decimal places down, but there's all the resistance.
So I don't need the length here.
No, you don't, not for the first part. Now, what does he want in the second part? So what goes on the x-axis? The length, and the y-axis? The OR. So let's make that graph. They said it as well, didn't they? So what type, this is called a scatter plot. So I'll just pop it in.
Even this time they will give us extra 10 minutes to see the paper.
Yeah, it's 2.5 hours plus 10 minutes reading time. This is question B6. On the x-axis is length in meters, and on the y-axis, resistance in ohms. Okay, and we'll put the line in as well, okay, because they'll want that as well. Okay, so that answers the graph part. Now for the next part, they give you the diameter and they want the rho. So if I go back here, now they tell us the diameter, so we know the area. Do we know the length?
Yeah.
Do we know the resistance?
Yeah.
Well, we actually know many resistance, don't we? So although they don't, they actually, no, sorry, they do say use the graph. So if you look at your graph, this is length. Wait, guys. Before you write, just concentrate here for one moment. This is length, and what's here? Resistance. So if you look at this, how could you rearrange this so that this, or what is the slope, I should say? Well, the slope is OR over L. So what is OR over L from this formula? Rho over A. So what does the slope equal? Rho over A. So the answer is whatever you got for your slope multiplied by the area. So if we go to the graph, what's the slope here? 0.629, and the formula for area is pi r squared. And what's the r? 1.1 divided by 2, because that's the diameter. I know, I'm not finished my sentence. 1.1 divided by 2. What are you asking me? 0.629. Yeah, because his slope, maybe it's estimated from the graph. I have an exact Excel value here. Does his graph look like mine?
Yes, exactly.
Yeah. So his is 0.5. Because you notice, KJ, these points don't perfectly line up, do they? So there's a allowable error. Anyways, pi r squared. And yes, Fahad, it's in millimeters, so then we put in -3. So if I go back here, if my slope was, what was it, 0.629 times pi r squared, and this comes out as 5.98 times 10 to the -7 ohm meters. Isn't that the unit for resistivity? So what's his answer? The 6. Okay, that's a little bit too different for me to be happy with, but who cares? Unless I wrote one of my numbers down wrong in my graph, but whatever.
Okay, yeah.
Right, last part now. Can I go down? Does he calculate the area? Yeah? Yeah, so, yeah, he used 1.1.
1.1 times 10.
But did he put in 1.1 divided by 2? Because
1.1 times 10 minus 3 squared divided by 4.
same thing then, yeah. Okay, fine. Right, next part. Describe an experiment to obtain the IV characteristics of a light-emitting diode. In other words, listen, they want you to describe experiment number 3 that you did for us. What was that experiment? Do you remember the circuit with the resistor and variable resistor? So, I'm not going to do it now because you did it already for me, but very quickly I'll just draw the diagram. What do we need? First we have a switch here, and then here is an ammeter, and then here is a variable resistor, and then down here a resistor. In this case they say use a light, and then there's a voltmeter, I know, that goes externally around the LED. And then you change this, which makes a change here, and this makes a change here, and then you make your graph. Let me just think. And you put the I here and the V here. So the only difference between your experiment and the experiment he's talking about here is that you put the I on the X and the V on the Y. What you'll discover is that if you use a ohmic, now we did this in the class, if you use an ohmic resistor, you get a straight line. If you use something like an old-fashioned light bulb, the light bulb will get hot as the current increases, and this affects the resistance, so then it flattens out. And then if you use something like an LED I think is pretty good, so I think an LED would be like a straight one. But some conductors, their resistance gets better as they get hotter. We don't do this in the course, but a semiconductor, a silicon conductor, like used in computers, they actually improve they have less resistance as they warm up, so their graph would go like that. So this would be something like silicon. This here will be a regular ohmic, and this would be non-ohmic. Oh, am I accidentally doing the next part? Draw the graph. Now,
I is on the Y side.
oh, I drew it the wrong way.
It is IV characteristics, not the
Hang on. Which experiment? Because you did this one. We did this in class. We talked about it in class. There is a lesson on our course called IV characteristics.
Yeah.
I'll tell you which one now.
I remember it.
Yeah, this is the lesson you need to remember. It's electricity, and it was. Hang on, KJ. We'll sort it out now. Which way does this graph go? He has the I on the X.
Is it graph or
Yeah.
diagram?
No, the graph for the very last part. Did I draw any graphs? Come on, I must have. Now you see, KJ, the slope is 1 over r. So the slope is, if I want the slope to be 1 over r, then I should have I here and B here, because the slope will be B over I, which is 1 over r. So that's why I put the I down below. Now in fact, it doesn't really matter if you do it the other way around, it just means your graphs will be opposite, which is fine. So if you put it like this, I had I and I had V, the graph will go like this for non-ohmic. But if you have it the other way around, V and I, the only difference is your graph will then increase at the end. So if he does this one.
Yeah.
What way does this graph look?
This way, but
It goes like this.
it said negative axis, no?
They said what?
Negative axis. Negative should negative.
Yeah.
Wow.
Oh, well, he does say in the question positive and negative. Hang on, that's okay.
Just draw this on the other one.
Yeah, so if you look here, so they want a positive and a negative. If this is a V and this is an I, so the graph goes straight and then it increases, curves up. Well, do you remember, what does negative voltage mean? It just means the current is going the other way. So if the voltage is negative on the voltmeter, then what happens on the ammeter? It's also negative. But do the numbers change when you swap the connection around? No, they don't. So literally it's the same, except you have everything as a minus instead of a plus. So it just goes like this then. Is that what he drew?
Yeah. But how do you know that this is a non-ohmic material?
I think the key is this: all materials are really non-ohmic because as soon as they warm up they produce more resistance. Now the thing about being an LED means that the graph should be straighter for longer. It would have to have a very high voltage and a lot of heat before it starts becoming non-ohmic, whereas an old-fashioned light bulb will very quickly get hot. So the only difference between an LED graph and an old-fashioned light bulb one is I'd have it increasing sooner. But of course that doesn't matter because there's no numbers on this graph, so who can tell what is soon and what is not. Alright, so that is another exam dusted.